You know, there's a lot of similarity between a diesel and a carbureted fuel system, but we'll take a look at some of the basic differences. In a carbureted engine, both fuel and air are pre-mixed, and this combustible mixture is ignited near the top of the compression stroke by an electrical spark. The speed and power of a carbureted engine is governed by regulating the amount of air and fuel mixture allowed to enter the cylinder. In a diesel fuel system, a full charge of air is taken in on each intake stroke. The fuel is injected later, near the top of the compression stroke, where it mixes with the air and is ignited by compression heat. The speed and power developed by a diesel engine is governed by the amount of fuel injected and the time available for mixing. Other ways in which these two systems differ, such as combustion timing and fuel burning characteristics, will be discussed as we go along. All diesel systems differ slightly in how they get the job done. But even though this difference exists, there are certain requirements they all must meet. By listing these requirements in a certain order, we can compose a definition of a diesel fuel system. It is one where fuel is supplied under pressure to the injection pump, which pumps and meters fuel to the nozzles with precision timing. The nozzles inject the fuel into the combustion area, where it is ignited by the temperature of the compressed air. Know these 8 requirements, and you can become a qualified diesel serviceman. Let's take each requirement and see how it is accomplished in the IHD 236 and D282 diesel engines. First, fuel is supplied to the pump. As the fuel leaves the tank, it passes through the water trap. Water must be removed before it reaches the pump. Otherwise, it will corrode everything it touches. As the fuel leaves the trap, it enters the hand primer, which is used to fill the system with fuel after servicing. As the plunger of the hand primer is raised to form a suction, fuel enters through a one-way valve from the supply line. Downward movement of the plunger closes the intake valve and opens an identical outlet valve. Fuel pumped from the hand primer passes to the primary filter. Here, fuel passes through a micronic paper element and foreign material is removed. The fuel then passes to a second or final filter where the process is repeated for further protection. The fuel, still under pressure from the hand primer, enters the pump through another cleaning device, the inlet strainer. This strainer catches paint or metal chips that might accidentally enter during servicing. In order for the fuel to reach the main body of the pump, it must bypass the transfer pump. This transfer pump will not allow fuel to pass through while it is stationary. To bypass the transfer pump, the fuel enters the end plate and passes through the pressure regulating valve, forcing the piston to compress the priming bypass spring. The piston uncovers a port leading to the discharge side of the transfer pump. The fuel enters the body of the pump, dispersing through and completely filling the pump. The fuel in a diesel system must be completely free from any air bubbles. Air bubbles under pressure give a spongy effect to fuel delivery, and precision metering is impossible. Misfiring results. To eliminate air bubbles, you must be sure that all connections and fittings on the suction side of the pump are both fuel and air tight. A fuel cavity at the end of the pump assists in bleeding off air during hand priming that may have entered the system while servicing. Near the top of the fuel cavity is an air bleed passage connecting the fuel cavity to the governor control housing, from where a fuel line leads back to the fuel supply tank. As air bubbles enter with the fuel during priming, they rise to the top of the fuel cavity, pass through the air bleed vent and are returned to the fuel supply tank where they escape. A wire installed in the air vent passage restricts the amount of fuel that can pass this way and helps to agitate the bubbles, keeping them moving. The second step in our requirements is to deliver this fuel under pressure. Gravity flow alone is not fast enough to completely fill the metering area for each discharge. Not only must we have sufficient pressure to charge the pump at its highest speed, but the pressure must also be uniform so that the charge received will not vary. Fuel passes through the end plate and enters the inlet side of the vane-type transfer pump. As the blades turn, the volume between the rotor and the inside diameter of the transfer pump liner decreases, and the fuel is forced into the passage leading to the pump. The blades have a wide notch in the middle to allow them to slide back and forth across the rotor as the distance between the rotor and the pump liner changes. This pump delivers far more fuel than is ever required for injection, so the surplus must be bypassed to control the pressure. The pressure regulator valve that serves as a bypass during hand priming also serves this purpose. The transfer pump pressure pushes against the piston and forces it to begin compressing the regulating spring. When the pressure reaches 65 pounds, it will have moved the piston far enough to uncover a port connected to the inlet side of the end cap. At this point, a circuit has been established that will remain open above 65 pounds pressure to allow the surplus fuel to be recirculated. If an increase in pump speed produces a greater volume of fuel, the piston is moved farther back, uncovering more of the opening, and a proportionate greater amount of fuel is bypassed. This simple system keeps the pressure almost constant, regardless of the pump speed. Transfer pump pressure can be adjusted higher by installing a longer plug behind the regulating spring. Installing a shorter plug would likewise reduce the pressure. Now that we have the fuel supplied and under pressure to the injection pump, our third step shows how the fuel is pumped to the nozzles. A look at the main parts show us how simply this is done. We have a drive shaft, a governor assembly, the distributor rotor, and the transfer pump blades. These parts all attach together and rotate as one. The distributor rotor assembly does the pumping. It is made up of a shaft with a fuel passage down the middle and two fuel passages to the outside of the shaft. At the drive end of the rotor are the pumping plungers, the rollers, and the roller retainers. The distributor rotor assembly fits into the hydraulic head assembly. The cam ring with the cam lobes on the inside fits over the rollers. The fuel under pressure from the transfer pump fills the fuel passage leading down one side of the pump away from the cavity at the end of the pump. From here, it fills a circular passage around the hydraulic head, where it connects to a passage leading to the metering valve. The fuel from the metering valve fills a passage in the hydraulic head surrounding the distributor rotor. 6 equally spaced fuel ports are drilled through the head from this circular passage to the distributor rotor bore. Whenever the pump is operating, these 6 ports and all the passages connecting them to the transfer pump are always full of fuel under pressure. As the distributor rotor turns, its charging port comes into register with one of the 6 charging ports in the hydraulic head. Fuel cannot escape from the other 5 ports at this time because they are sealed off by the close fit between the distributor rotor shaft and the hydraulic head. While these 2 ports remain in register, fuel flows through the charging passage and enters the chamber, moving the pumping plungers outward. As the distributor rotor continues to turn, the charging ports pass out of register and the discharge port of the rotor comes into register with one of the fuel passages drilled through the hydraulic head and connected by a fuel line to each of the nozzles. At the same time the discharge port comes into register, the rollers of the pump come into contact with lobes on the cam ring. This force on the rollers pushes the plungers toward each other, squeezing the fuel out of the rotor shaft and through the line to the nozzle. Two grooves in the rotor, one on each side of the rotor charging port, deliver a substantial quantity of fuel from the 6 hydraulic head charging ports into the pump housing. The fuel flows through the entire pump housing, lubricating the cam, rollers, and governor parts. This system always supplies fresh, cool, filtered fuel, and a special oil pump is not necessary. The fourth step of the pump is to meter the fuel. Metering, or pumping a measured amount of fuel, is the way we have of controlling the speed and power of the engine. Remember, at the very first, we said that a diesel engine always takes in a full charge of air on each intake stroke. With no load on the engine, the more fuel we pump to the engine, the faster it will run. In the pump, we regulate this fuel supply with the metering valve. The metering valve is placed in the fuel passage between the transfer pump and the charging ports, controlling the amount of fuel able to reach the distributor rotor. Turning the metering valve brings more or less of the opening into register with the fuel passage. The metering valve position is changed by spring pressure through the governor. The operator's throttle controls are connected to the throttle arm and shaft at the pump. When the operator opens the throttle lever inside the pump compresses the governor spring. This spring pushes on the governor arm, which in turn pulls on a small spring attached to the linkage hook. The linkage hook opens the metering valve and the engine speed increases. Then, the centrifugal force of the governor weights balance the compression of the governor spring, and the governor arm moves the governor linkage hook to hold the metering valve partially closed. High idle engine speed is adjusted by a stop screw that limits how far we compress the governor spring. Low idle is controlled by an adjusting screw that keeps the throttle lever from releasing all the pressure on the governor spring. As the engine begins to pull a load, it slows down slightly, and the governor weights do not fly out with as much force. This lets the governor spring open the metering valve to deliver more fuel, and the engine fights back against the load. When the point is reached that the pump is delivering more fuel than the engine can burn, the exhaust will begin to turn black. Black smoke is a sign that the engine is receiving more fuel than it can burn. To prevent the metering valve from increasing fuel supply to the engine beyond its ability to efficiently burn it, there's a simple stop screw adjustment. When the load pulls the engine down to rated load speed, the metering valve is opened as far as the stop or torque screw will allow. The torque screw then should be adjusted to let the engine have all the fuel it can efficiently burn. This point will be when the exhaust turns to a light haze. Allowing the smoke to turn black at rated load wastes fuel and decreases the engine's efficiency. At certain times, the load on the engine will increase beyond the normal or rated load amount. When this happens, one of the most desirable features of the diesel engine begins to take place: torque backup. Torque backup might be referred to as the engine's ability to pull or lug harder under overload. This increase in lugging ability comes from two things. First, an increase in volumetric efficiency of the engine, which simply means that there is more time available to mix fuel and air. And second, because of this, greater quantities of fuel can combine with air, forming a combustible mixture, and more power is developed. Our pump answers this call for more fuel in a very simple and foolproof way. Even though the torque screw will not let the metering valve open any farther, we can still supply more fuel to the pumping chamber during these overload periods. The pump is engine-driven, so when the engine pulls down, the pump slows down too. As the pump turns slower, the charging ports of the hydraulic head and the distributor rotor stay in register for a longer period of time. This means that the fuel, still under pressure, has a longer period of time to fill into the pumping chamber. As a result, the pumping chamber is charged with a greater amount of fuel and more fuel is injected. Just as we limit the metering valve with the torque screw at rated load, we must also limit the amount of fuel taken into the pumping chamber during an overload condition. A leaf spring assembly is attached to the distributor rotor and overlaps the edge of the roller retainers. Thus, the pumping chamber can only fill until the plungers and rollers move out to the point where they are stopped by the leaf spring. Adjusting the leaf spring is simple. Tightening the mounting and adjusting screw in the middle will flatten out the spring and spread the edges. This would let the plungers move out further in the chamber and allow more fuel to enter. To reduce the amount of fuel supplied under overload, turn the adjusting screw counterclockwise. This lets the leaf spring contract, holding the plungers in farther. All adjustments for rated load and overload conditions are based on correct governor spring tension and accurate high idle speed adjustment. In addition, a well-informed serviceman will know that the grade of fuel, temperature of the fuel, and the temperature of the air being taken into the engine will all influence the fuel adjustments. To stop the engine, we merely shut off the fuel supply. When the operator pulls the shut-off cable, it rotates the shut-off arm and cam. The cam moves the governor linkage hook, which turns the metering valve to shut off the fuel. The timing relationship between the injection of the fuel and the relative position of the piston on the compression stroke is the fifth step. As you remember in the carbureted engine, the fuel and air are mixed before entering the cylinder to form a chemically correct combustible vapor. This mixture enters the engine on the intake stroke, and when the spark plug fires, the entire mixture burns almost at once. Since this mixture is already correct for combustion when it enters the engine, it will ignite any time the spark plug fires. This principle does not apply to the diesel fuel system. In the diesel system, only the air enters on the intake stroke and is compressed by the piston. When the fuel is injected near the top of the compression stroke, it must first combine with the air before it will ignite. Ignition begins as soon as any part of the fuel has combined with enough air to form a combustible mixture. Injection should always begin at the same time, but it will end at different times, depending on how much fuel is to be injected. More torque is developed by a diesel engine when ignition continues as long as possible. As the piston begins to travel down, leverage on the crankshaft increases, reaching its maximum at 90 degrees to the cylinder. Timing then becomes very important so that the fuel can be injected and mixed at compression temperatures suitable for ignition. When we retard the pump timing, we get a white exhaust smoke, which indicates that some of the fuel is not being burned, but just being vaporized and puffed out the exhaust stack. On the other hand, if we advance the pump timing, we rapidly lose our leverage advantage on the crankshaft. Excessive pressures are created during combustion and black exhaust smoke may be present, making it very difficult to make accurate fuel adjustments. To make this precision timing easy for the serviceman, lines have been provided on the governor weight retainer and the cam ring. With the engine set at the proper timing position, the serviceman has only to turn the pump so that these two marks are aligned. In the Rosa Master Pump, injection begins when the rollers contact the lobes of the cam ring and are squeezed inward. Injection ends when the rollers reach the top of the lobes. As the charge of fuel increases for heavier loads, the pumping plungers move the rollers out farther. Since the rollers have moved out further with the increased fuel charge, the cam must be rotated a few degrees in the direction of rotor rotation to keep the start of injection timing the same. This rotating of the cam ring takes place here, inside the automatic advance. With a cutaway view, we can see that on one side a spring-loaded piston is pushing against the cam advance screw. This spring pressure holds the cam ring in the retard position, or position for injecting the most fuel. A special notch in the metering valve directs some of the fuel pressure into a fuel passage around the other side of the pump, where it can enter the automatic advance through the advance body clamp screw. When the engine is operating under no load and little fuel is required, the metering valve is turned to allow enough fuel pressure to reach the power piston, overcoming the spring pressure and moving the cam ring to the advance position. Now, as a load is applied to the engine, the metering valve turns to let more fuel pass to the charging ports, and the fuel pressure to the automatic advance is reduced a proportionate amount. As the fuel pressure to the automatic advance decreases, the spring piston automatically retards the cam ring to keep the start of injection the same. Every time the rollers come into contact with the cam ring, the pressure between the two attempts to make the cam ring move into a retarded position. This pressure is great enough to overcome the pressure behind the power piston and push it back. To prevent this pressure from affecting the position of the cam ring, a check ball and spring are located in the pressure passage of the automatic advance. This ball restricts flow of fuel away from the power piston, thus preventing the force of the roller against the cam from retarding the cam. The clearance between the power piston and the advance housing allows enough fuel to leak by to let the spring piston move the power piston back whenever pressure from the metering valve is decreased. A flat side on the spring piston prevents it from trapping fuel behind it, developing a hydraulic lock. A method has been provided to allow us to adjust the position of the metering valve and regulate when fuel pressure will be diverted to the automatic advance. A pie-shaped notch running lengthwise to the valve has been cut out to make a passage for the fuel to the charging ports. Near the top of this notch and on the opposite side of the valve is a smaller notch cut crosswise to the valve. This notch diverts fuel to the automatic advance. The metering valve is supported by a small coil spring. Directly over the metering valve is the governor spring guide stud. A beveled surface of the guide stud contacts the chamfered top of the metering valve. The height of the metering valve can be adjusted by turning the guide stud in to lower or out to let the spring raise it. As the engine calls for more fuel with the valve in a high position, the opening of the metering valve cuts off the fuel pressure to the automatic advance very soon, and the spring pressure on the cam would begin retarding it almost at once. With the guide stud turned in farther to lower the metering valve, greater loads are required to open the metering valve far enough to cut off fuel pressure to the power piston. Through this simple adjustment, we can regulate at what engine load the cam will retard, thereby controlling the start of injection and keeping it constant. Now we come to the sixth step, the injection of the fuel. Injection is accomplished at the nozzle. The injection nozzle itself is contained inside the nozzle body. This rugged body helps to absorb and disperse heat away from the working parts of the nozzle. 6 simple parts make up the nozzle: the valve cap, the valve retainer, the spring, the spacer, the valve body, and the pintle. The pintle is held tightly on its seat in the valve body by the pressure of the spring, pushing against the valve retainer to which the other end of the pintle is hooked. When fuel pressure against the pintle valve becomes greater than the combined pressure of the preloaded spring and the pressure in the combustion chamber, the pintle moves outward and fuel flows past. The maximum outward movement of the pintle is controlled by the valve retainer contacting a shoulder within the valve body. A nozzle opening pressure has been established that utilizes the design of the pintle and orifice to obtain the best fuel penetration and atomization into the compressed air. During service, care should be taken to maintain uniform nozzle opening pressure so that fuel delivery to each cylinder will be uniform. Nozzle opening pressure can be adjusted by interchanging the spacers, which have various thicknesses of shoulders and will increase or decrease the amount of preload on the nozzle spring. To prevent nozzle dribbling after injection, it is necessary to drop the pressure in the injection line below the opening pressure of the nozzle immediately at the end of injection. This lets the spring snap the pintle closed and cuts off the injection sharply. This drop in line pressure is done for us by the cam ring. Just before the discharge port of the distributor rotor passes out of register with the fuel passage to the nozzle, the rollers reach the high point of the cam lobes. From this point, the cam ring lobe is ground back slightly to allow the rollers to move out just enough to drop the line pressure before the discharge port is sealed off. It's also necessary to maintain some line pressure between individual injections. This pressure must be below the opening pressure of the nozzle, as was already explained, but it should be high enough to eliminate the necessity for the pump to build the line pressure up from zero for every injection. How far the line pressure drops when the roller reaches the relieved portion of the cam lobe is limited by a displacement-type delivery valve located in the distributor rotor just ahead of the fuel discharge port. When pressure is created in the pumping chamber and fuel is forced from the distributor rotor to the nozzle, this displacement-type valve opens in the direction of fuel flow and allows fuel to pass through. The total movement of the valve is controlled by a stop which contacts the top of the valve. When injection ends and the cam relief allows the rollers to move out and drop the line pressure, this valve moves back to its stop, displacing the same volume of fuel in the line and sealing off the remaining pressure in the line. Leakage is prevented by the valve fit in the rotor bore. The rollers may continue to move outward slightly, but the line pressure is not affected because the delivery valve prevents the return of fuel. The size and total movement of the delivery valve is designed to allow sufficient line pressure drop to prevent nozzle dribbling, but to limit the pressure drop and maintain even line pressure at all nozzles. The seventh and eighth steps are ignition and temperature. Ignition takes place instantaneously when the fuel is atomized by the nozzle and enters the high temperature air in the pre-combustion area. Efficient combustion depends on temperature and complete mixing of the fuel and air. Turbulence is the answer. Here the pre-cup is at an angle to the cylinder. This position and the angle of the throat makes the air set up a violent whirling motion as it is compressed. In order for a diesel engine to start, it is necessary for the temperature of the compressed air to be about 1,000 degrees Fahrenheit. Compression of the air will provide some of the heat required for starting, but an electric glow plug extending into the pre-cup further heats the compressed air. The pre-cup is heat insulated too, with airspace all the way around to help maintain heat which is essential for good combustion. Well, there you have the 8 essential requirements of a diesel fuel system. First, the fuel is supplied under pressure, then pumped and metered at the correct time. It is then injected and ignited by the temperature of the compressed air. Once these fundamentals are thoroughly understood, a serviceman can utilize the information contained in the Blue Ribbon Service Manual to perform qualified service on the IH diesel engine.